Hello. In this video, we'll be talking more about section 2.3, Systems of Linear Inequalities in Two Variables. In this situation, we're going to be looking at a system of linear equalities, meaning we're going to be looking at multiple inequalities and finding the consistent solution set that satisfies both of them, or more so if we have multiple inequalities. So, to demonstrate this, we have this example here. Y greater than negative x and y less than 2x plus 5. First of all, we think about each inequality separately. So, on the left side, we have y greater than negative x, represented by the equation y equals negative x as our boundary line, which is dashed because we do not have an equality there. And we then have the shaded region above that to represent the half plane of solutions. You can test this as usual by plugging in a point, such as here 1, 0, which would be about there, to see if that would work. Same thing for y less than 2x plus 5. We have here a line drawn at y equals 2x plus 5. Again, dashed, however, because we do not have those values included. And we have the half plane to the right of it that is shaded, and we can test that by testing something like 0, 0, and seeing if that point would satisfy this inequality. In order to find the set of solutions that would satisfy both of these inequalities, we can graph them together, which is shown on this graph here on the right side. Both are shaded with the same colors, red for y less than 2x plus 5, and blue for y greater than negative x. And wherever we have solutions that are in common for both of them, that should be where they overlap and are solutions to the full system. We can even test points within that region if we need. They demonstrated and tested the point 3, 1 and found that they both work for both of the inequalities in this case. So let's see a couple examples of how that would work. In this example, which is a guided example, we have the system 2x plus y less than 3 and y greater than or equal to x plus 3, and we're going to solve this by graphing. We will change the equations first into slope-intercept form to make them easy to graph, or you can find the intercepts however you prefer to go about it. If you take 2x plus y less than 3 and you subtract 2x to the right side, you will get this in slope-intercept form for an inequality as y less than negative 2x plus 3. We can then graph the equality version of this, y equals negative 2x plus 3, and we'll do so with a dashed line because we have a less than for the inequality we're testing, not less than or equal to. With this slope-intercept form, that tells us that we have intercept at y equals 3, so at y equals 3. And we have a slope of negative 2. That means we're going to go down 2 for every 1 that we run. So down 2 over 1, or up 2 back 1, however you want to think about it. This should give us our boundary line for the inequality y less than negative 2x plus 3. I will graph this, but I'll again do so as a dashed line. Just like that. As for the second inequality, we already have this in slope-intercept form, y greater than or equal to x plus 3. And again, we're going to graph the equality version of this, y equals x plus 3, to represent our boundary line. This one also has a y-intercept at 3, so they do already have that point where they overlap. But it has a slope of 1 in front of x, so that'll be up 1 over 1, or back 1, down 1. This one, though, we will graph as a solid line because the equality there is greater than or equal to. So something like that. Now we need to test points. We essentially need to see where they both overlap. Let's go ahead and look at the blue inequality here. With the blue inequality, we can test a point on either side of that and see where it works. I like to test 0, 0, so I'm going to test 0, 0 here. If I do, I will plug in 0 and 0 for x and y. I'll get 0 less than negative 2 times 0 plus 3. Negative 2 multiplied by 0 is just 0. And I get 0 less than 3, which is a true statement. That means everything where 0 and 0 would work that means everything on the side of the dashed line that includes 0, 0 would be a set of solutions for that first inequality. So I'll graph that in blue here. Just like that. Then for the red graph, we can also test something. And again, I just like testing 0, 0. So I'll just test 0, 0 here and see what side of the red solid line would represent solutions for that inequality. If I put 0, 0 into that red inequality, I will get 0 greater than or equal to 0 plus 3, giving me 0 greater than or equal to 3. This one is not true. 0 is not greater than or equal to 3, which means that we would want the half plane that is not including 0, 0 to represent the set of solutions for the red inequality. So I'll shade that in red. That would be everything above the red line. Just like that. In order to find the solutions that would actually work to represent the graphical solutions here, we want where we have an overlapped region. That overlapped region here would be on this corner. The side that is above the red inequality and the blue side that is to the left of it. That overlapped region would represent my set of solutions. Note that this specifically would include values that are on the red line, but not include values that are on the dashed blue line. By the way, this also means that the point where these two intersect there, which is at y equals 3, would not be included because it is on the red solid line, but it technically is also on the dashed blue line, which should not include values. So we do not include that point there where they intersect. That should be all for now. Hopefully that helps you understand how we will work with a system of linear inequalities to find a graphical solution. Have a nice day.